Hi, this is Professor Dan Kernler, and this is our last video in section 16.5. We're looking at triple integrals, and we're going to do two last examples, and we're going to try to set these up and maybe do one for each. We're going to try to set up in all three coordinate systems and then maybe pick one to do for each of these. We're going to try to find the first one here, the triple integral that gives the volume of the solid region bounded by z equals 2, and then above by this hemisphere. So what we have is x, y, z. We have a hemisphere of radius 5. And then we have z equals 2 is a plane that we're going to cut this off right here. Right? And we're just going to look at the top portion of this above z equals 2. Okay, well, let's see here. Let's do some investigation. Let's find out where those two surfaces intersect. So let's do square root of 25 minus x squared minus y squared equals 2. That's 25 minus x squared minus y squared equals 4. X squared plus y squared, if we add that to the other side and subtract, equals 21. So in the xy plane, we would be integrating over the circle radius square root of 21 centered at the origin. Okay, well, since I have all these x, y's, and z's, let's do rectangular first. Okay. I'm going to start on the inside. Z goes from the plane up to the hemisphere. So z goes from 2 up to square root of 25 minus x squared minus y squared. That's dz. And then I guess we can go y next and then x. You can see over here in the circle, y is going to go from the bottom half. So negative square root of 21 minus x squared to positive square root of 21 minus x squared. And then x will go from negative square root of 21 to positive square root of 21. Okay, so some crazy bounds. The integrand itself looks pretty simple to integrate the first step, but then you're going to have square roots integrating square root of 25 minus x squared minus y squared. I will pass on that one. Let's try cylindrical. There's two ways to do this. We can substitute within the current integral that we have. That's one way to do it. I like to start here. We're going to have dz again, but we can't have x's and y's, so we need to rewrite any of those in terms of r and theta. So, but z goes from 2 to the square root of, and then it'll be 25 minus r squared. 25 minus x squared plus y squared, if you put that in parentheses. So 25 minus r squared. And then we have an r, dr, d theta in there. R, well, it's just a circle. R goes from 0 to square root of 21. And then theta goes from 0 to 2 pi. Doesn't look too bad. I think spherical on this one is actually like not easy because it's hard to get a constant z value of 2. So let's take a look at that from the side. Let's look at y or x. I guess it doesn't really matter, x or y. And then z. We have this 2. I need a little bit more height here. Z, and then we have the portion of the hemisphere. This we know here is rho, and rho is equal to, I guess we actually, that's just, this is just 5, right? But that's the, yeah, that's just the outer row, there would be 5. We have to find some expression for this inner row. We know that z is equal to 2. We know in spherical coordinates z is rho cosine phi. And so I guess we could divide 2 over cosine phi And so, or we could say 2 secant phi. So that's how you get a constant z equals 2, is you have 2 secant phi. So integrating here then, let's scroll down a little bit. Rho, let's see, we have rho squared sine phi, rho d phi d theta. And rho will go from 0 to 5. No, not 0 to 5. We just did this analysis that goes from 2 secant phi up to 5. Phi itself starts at 0 and will go down until, I need another color here, until that edge, whatever that phi is, phi not theta, that's the maximum one it'll get to. So phi starts at 0, and let's take a look at that one. That'll be, let's see, here we have phi, and then this will be 2, and what else? I guess we have to know, well, we know that radius. We know that radius, that's the circle where they intersect. If you project that down, that's square root of 21. Aha. So we can go tangent phi equals square root of 21 over 2. So phi will be equal to arctangent of square root of 21 over 2. Okay. So I'm just going to write tangent inverse because I don't have a lot of space. Square root of 21 over 2. And then finally, theta does need to go all the way around. So that's 0 to 2 pi. I don't know. Do we want to do, maybe cylindrical feels like the easiest to me. None of those look great. Let's try here. We're only 7 minutes in. So let's try cylindrical. Let's see here. Integral of 0 to 2 pi, integral 0 to square root of 21, and then integral from 2 to square root of 25 minus r squared. And then that's r dz dr d theta. Okay, so let's do z first. That's just going to be rz from, almost did 0, from 2 to square root of 25 minus r squared, dr d theta. And that's just 0 to 2 pi r times square root of 25 minus r squared minus 2 dr d theta. What do we think? We do a u substitution right now? I think we probably can. Let's do u equals 25 minus r squared. du is negative 2r dr. We have an r dr. We'll do negative 1/2 du equals r dr. U at the lower bound. Whoops, I lost my 0 to square root of 21. U at 0 will be 25, and then u at square root of 21 will be 4. So this is another one of these where it looks like we're going to switch directions. So we would have negative 1/2 integral 0 to 2 pi, integral from 25 to 4, and then we have square root of u minus 2 du d theta. Or we could make it positive 1/2 and then switch the bounds 4 to 25. Okay, now we'll integrate 1/2 integral 0 to 2 pi. Integral of square root of u will be u to the 3/2 times 2/3 minus 2u from 4 to 25. I'm going to let you compute that on your own. It actually, not coincidentally, but it actually works out really nicely. You just get 36. And after all that, you end up with 36 pi when you're done. And I'll let you do those steps there on your own. A little bit of Calc 1 there to finish it out. Okay, last one, and let's just practice setting these three integrals up. Let's do that. We have, let's see, triple integral of the volume of the ice cream cone bounded by a sphere. Oh, and then a cone. Okay. Should have had maple up for this. That would be useful, but that's okay. Sphere, radius 2, cone, square root of x squared plus y squared. See, that one looks like if you square both sides, z squared equals x squared plus y squared. And if you set say x equal to 0, you get z squared equals y squared. So z is plus or minus y. And then if you set z equal to specific values, like say z equals 1, you get circles. That would be x squared plus y squared equals 1. So those are, they're lines in the xy and then circles in the z. And then you have this sphere, part of it here, sphere radius 2, that is the top portion of this, that's your ice cream. It's not a hemisphere really, it's just a truncated part of it. So looks like, just like in previous ones, we need to find where do these intersect. We need to figure out where do these intersect. I guess we'll have to solve for z in the hemisphere. So that'd be square root of 4 minus x squared minus y squared. And actually, I keep saying hemisphere, but it's in the sphere, in the ice cream part of it. And then we'll set that equal to the other one, square root of x squared plus y squared. Oh, this is nice. Square both sides. 4 minus x squared minus y squared equals x squared plus y squared. Oh, very nice. Add the x squared plus y squared. 4 is equal to 2x squared plus 2y squared. And so you get x squared plus y squared is equal to 2. Circle radius square root of 2. Okay, so rectangular. We'll integrate from the cone to the ice cream. So the cone to the portion of a sphere. That'll be z. The cone is square root of x squared plus y squared. And then the part of the sphere, square root of 4 minus x squared minus y squared. That's z. And then we might as well do, this is like the last one, maybe just pick y. And so y goes from negative square root of 2 minus x squared to positive square root of 2 minus x squared. And you could just as easily do x there. It would be exactly the same. And then x goes from negative square root of 2 to positive square root of 2. So there is rectangular. Let's do, that's rectangular. Oops. Let's do cylindrical next. I feel like that one's similar to this. We would still do dz, and then now that would be square root of r squared, which would be r, to the square root of 4 minus r squared. Okay, doesn't look too bad. And then we have r dr d theta. We're integrating over a circle again, which is nice. R goes from 0 to square root of 2, and theta goes from 0 to 2 pi. Yeah. Seems pretty straightforward. I think we could probably do that. That's pretty similar to the last integral. Spherical coordinates, let's check that out. Let's see here. So somehow we have to get spherical. R has to, let me kind of look at this from the side again. This would be the x, y, either one. We have the portion of a sphere, and then we have the cone. Okay. Oh, but the cone is actually just determining the feet. So rho Need to go a little bit lower. We have rho squared sine phi d rho d phi d theta. Rho goes just from 0 to 2. Interesting. Okay, then phi, we have to figure out where do they intersect, right? Let's see, this is 2. Oh, and then if you drop down, that's the circle. This is square root of 2, right? Whether it's on the x-axis or the y-axis. So what, that's 45, right? So 0 to pi over 4. And then theta has to go all the way around 0 to 2 pi. Nice. That seems manageable. Let's try that spherical one. I was just going to set these up, make the video a little bit shorter, but you know, you really want to watch me go all the way through this. So you could stop here if you want, but I'm going to continue through, and then I'm just going to hint at a really special, important announcement at the end. We're going to integrate rho, so that's rho cubed over 3 from 0 to 2, sine phi d theta. That would just be 8/3 sine phi d theta. And let's see, again, negative 8/3 cosine phi from 0 to pi over 4 d phi, nope, we integrated phi, d theta. Cosine of pi over 4, square root of 2 over 2 minus 1 d theta. And we'll just multiply that then by 2 pi, because you integrate, you get theta from 0 to 2 pi, so you end up multiplying this by 2 pi. So I'm going to do this, 8/3, and then just change the order, 1 minus square root of 2 over 2 times 2 pi. So what that means, I just factored, like distributed the negative 1. Makes the square root of 2 over 2 negative, makes the 1 positive. I feel like I should do better than that. I don't know. Oh, too much. 16 pi over 3 and 2 minus square root of 2 over 2. So 8 pi, 2 minus square root of 2, 8 pi over 3. I don't know, that's about as good as I can get. That looks pretty good. And that is the volume of this ice cream cone. Now that includes the cone itself and the ice cream on top. So if you stuffed ice cream down into the cone, that's the total volume of ice cream you'd have, and cone, because the cone takes up some volume too, right? Okay, so that is it for this video. There's no important announcement. Sorry, I just wanted to make you watch till the end. And that is it for section 16.5. That was a doozy. We will see you in the next video.